All right, so do me a favor and take a look at the cover kind of chart title page for a second. This Unit 4, it's pretty important, I'd say. We're going to start to apply derivatives. If you look at the name, okay, application of the derivative, we've been talking about shortcuts, we've been talking about how we can find the derivative, but now we're actually going to talk about why we want to do this. Okay, why is a derivative important to know or to know how to use? So we're actually going to apply what we've been talking about. This unit, if you pick it up, it feels a little thick. Okay, but when you take a look at the title page, there aren't that many sections. We have the first two sections at the top. And then we're going to have a kind of a free response day. Now, we haven't had one of these yet in this class. The pre-calc class has had a few. But this is going to be a day where we're going to practice free response questions. You're going to see some that we kind of tackle together as a class throughout the notes or in the notes. But on this day, I want you to tackle some together, like in little groups. Not so much using me as an aid, I want you to talk to each other. Unfortunately, I'm not going to be here for this day. Okay, my last day is Tuesday or Wednesday, I'm not quite sure, next week. So it's coming fairly quick. What we're going to be able to do in the meantime is we're going to finish the first section, probably today and tomorrow, and we're going to start the next section together next week. But Mr. C, my sub, will kick off with you guys starting here. Okay, and I'll be back beginning of March. I'm an email away. Okay, if you need help with anything, just email me and let me know. I'm not sure if many of you view the videos online that I record in class, but if you need me to create something for you, maybe Mr. C knows his stuff. Okay, he's good to go, but it just might not be what you're used to or what your preference is. So if you need something from me, you just let me know and I'll try my best to get it to you. Okay, I'm an email away. We understand that? Okay, so I will be leaving halfway through this section and then he's going to take over from there. This unit, since it's pretty important, we're going to break it up. We're going to have a unit test just after these first two sections. Okay, that's it. And then we're going to have another unit test after these two sections. Okay, so even though the sections there aren't many sections, we're going to spend some time on them. Notice how this is going to take us about 3 or 4 days, and this one might take us about 4 or 5. So we're going to spend some time talking about these topics. Okay, so Unit 4, pretty important, applying a derivative. We're going to break it up into two parts. Okay, so today we're going to talk about differentiating, okay, finding the derivative of equations that are implicitly defined. Maybe you've never seen these types of equations before, so that's what we're kind of going to discuss first. Okay, what on earth is an implicit equation? So we're going to start on page 201. In your mathematical career, you are always used to seeing f of x equals y equals g of x equals something like that, right? Okay, y equals mx plus b has been beaten into your brain since pre-algebra. Okay, it's usually always y equals something. Okay, that's what's referred to as explicit form. The y variable is explicitly or exactly equal to something in terms of x. Okay, that's what's referred to as explicit. Y equals something. You could also have x equals something. In that case, x is explicitly equal to another variable. Implicit, on the other hand, is an equation that looks like this. Do you notice how the x's and y's are kind of all mixed in? It doesn't say y equals something or x equals something. You have x squared plus y squared minus 2x plus 4y. A bunch of stuff kind of jumbled together. So explicit is what you're used to, whereas implicit has the variables mixed throughout. Okay, there's a difference between the two forms. So what we're going to do is we're going to practice finding derivatives of implicit equations. We know how to find the derivative of this, okay, using some of our shortcuts. What we're not quite familiar with is how do we find the derivative of this? How do you find the derivative of x's and y's when they're kind of mixed together? So we're going to take a look at that in this section. Okay, one thing that you're going to see pop up a lot is this symbol, dy over dx. Have I mentioned that before in here? Very briefly, because we haven't really used it a lot. Maybe you've seen it in some places. Dy over dx is the same thing as f prime. Okay, it's another symbol that just means derivative. Did I show you where this comes from? Dy over dx? How it's related to slope? Okay, maybe I'll do that real quick. We know slope is y2 minus y1 over x2 minus x1. Scientifically, maybe you've seen triangles before, like delta y over delta x, a change in y over a change in x. But in terms of calculus, we use dy over dx. Okay, so we know a derivative, aka f prime, is slope. We know this slope formula. We know changes or in terms of triangles means slope. So dy over dx is just another way to rewrite it. All right, so dy over dx is the same thing as derivative. It's just a different symbol. Remember when we talked about Newton and Leibniz, the two people that created calculus? Okay, one guy used this notation, whereas the other one used that one. Okay, they both mean derivative. So let's go ahead and practice this. So we have the explicit equation that we're used to, and then the implicit is where we have the x's and y's kind of mixed in. Okay, so we're going to take a look at this explicit versus this implicit one towards the end of that paragraph. All right, let's talk about derivative. How would you find the derivative of the explicit? How would you want to represent the derivative of y? How do you represent the derivative of f of x? F prime, okay? But notice how this isn't labeled f of x equals. Okay, even though f of x and y are the same thing, this doesn't say f of x equals, this says y equals. So in terms of notation, we're not going to say f prime. What symbol or notation can we use to represent the derivative of y? Yeah.
Y prime.
You could use y prime. Okay, I think you saw that on the unit test perhaps. Okay, y prime, that's one thing you could use. But you could also use this dy over dx. This is just symbolizing or signifying the derivative of y, okay, the change in y as there is a change in x. So for this section, I would prefer that you use dy over dx. You could use y prime, but when we start to go through some examples, the y prime is going to get a little confusing, okay? And I'll show you why in a little bit. But for dy over or for this section, dy over dx is going to be a little bit more organizational for us. So the derivative of y, we can just say dy over dx is that notation. How do you want to figure out the derivative of the right-hand side? Think about your shortcuts. We just have x's in this one, so we can think about some of those shortcut ways. Yeah?
We could use composite rule, as we know that the square root of the inside is going to be just e to the power 1/2.
Okay, so composite rule, aka chain rule. Let's go ahead and rewrite the square root as a power. So think about your chain or composite. Composite just means one function inside of another. How would you go about the chain rule from here? Yeah?
You'd have 1/2 in front of the inside in parentheses, so basically replicating the top.
Okay.
And then you'd have negative 1/2.
Deal. Okay,
And
keep.
then you'd multiply the whole thing
Uh-huh.
by the derivative of the inside, which 25 just goes away. And
Yep.
you get negative 2x.
Negative 2x. All right, so the chain rule, we have the derivatives of those layers. Okay, outer layer chipping away towards the inner layer. I like this. Can we clean it up? Are some things going to cancel? Are some things going to move? What do you want to do, Dan? Yeah.
The negative 2 and the 1/2
Uh-huh.
will cancel out through math, so you can just have x on the top alone.
How about the negative?
Negative x.
Okay,
on top
good.
alone.
Okay.
And then you can divide the negative x by the square root, because
Mm-hmm.
the negative exponent would become positive square root of 25 minus x squared.
There we go. All right, so 1/2 times negative 2 is a negative 1. We're still left with an x. That would be in top of a fraction. Since we have a negative power, that would move to the bottom of a fraction. 1/2 power symbolizes square root, okay? So the derivative of this explicit equation, okay, y equals something, okay, you're used to seeing that type of equation. We have this derivative, okay? Let's go ahead and see how we're going to tackle an implicit equation. Now, notice how, perhaps, that this implicit equation is actually the same exact thing as this explicit. Okay? If you tried to solve this one for y, wouldn't you have to subtract the y squared over? You don't have to write this down, I just want you to realize this. Okay, we would subtract the x squared over and then square root both sides. Technically, we would need a plus or minus, but isn't this y equals a square root of 25 minus x squared, just like this one is? Okay, so these two are the same exact equation, they just look different. One is in explicit form, one is in implicit form. So if they're the same exact equation, we should get the same exact derivative. Does that make sense? But they just might look different because this equation looks different than this one. So let's go ahead and try to tackle this derivative. How would you want to find the derivative of x squared? Thinking about your shortcuts. Yeah.
Probably just use the power rule and get 2x.
You get 2x power rule. Okay. How do you internally, okay, want to find the derivative of y squared? I know we haven't really done derivatives of y's, but is there something like intuitively that you feel like doing? Yeah?
Power rule?
Power rule, okay? It would be 2y, right? Just like the other one was 2x. Now here's the kicker, okay? We just took the derivative of a y variable. What symbol or notation do we have to use to signify that? What represents a derivative of y? Yeah.
dy over dx?
A dy over dx. So after you find the derivative of a y variable, using any of those shortcuts or techniques that we talked about, we must also write a dy over dx. Because in this case it was a y variable, not an x variable. Can you think about why we don't need 1 over here after we take the derivative of x? Can you think about it? Like, what would this look like? If I were to write something after that 2x, what would that look like? Yeah?
Just be dx over dx.
Okay, we took the derivative of an x variable. Okay, so this is representing a change in x over a change in x. Dx over dx simplifies to 1, right? So why even bother writing it if it's just going to simplify to 1 anyway? So moral of the story is we only have to write dy over dx whenever you take the derivative of a y variable. Okay, let's go ahead and write that down kind of off to the side here. Dy over dx for every derivative of y. Okay, we're going to spend a lot of time practicing this through some examples. But whenever you take the derivative of a y variable, you must immediately write a dy over dx after it. Okay, let's continue through our equation. We took the derivative of x squared, we took the derivative of y squared, remembering that dy over dx. What about the other side of the equation, the derivative of 25? Pretty simple. We got 0. Okay, so here's what the initial kind of derivative looks like, but just like the other one, we should try to clean it up a bit. Okay, notice how over here we have dy over dx, okay, the derivative equals something. We're going to try to do the same thing over here. We're going to get this dy over dx equal to something, meaning we're going to solve for dy over dx, get it by itself. So what are some algebraic steps you want to use to get this dy over dx symbol alone? Can we start to move some things to the other side? Yeah.
You could subtract 2x and get 2y dy over dx equals negative 2x.
Okay. And then what else do you want to do to get this dy over dx all by itself? Yeah.
Divide by 2y, which could just become negative x over y.
All right, so the 2's would cancel and we would have a negative x over y. There's our final derivative. Okay, these two are exactly the same. They just look different. In the explicit form, don't you notice y equals this square root value? And if you were to take that square root and plug it in for that y, wouldn't it match this one? Exactly. Okay, so we are finding the same derivative, okay, using shortcuts we know. It's just we're starting with an equation that looks a little different. We have x's and y's mixed in this time instead of it being just a y equals equation. Okay, so implicit, we're going to use the same shortcuts that we're familiar with. The big thing is we need a dy over dx, okay, that symbol, for every time we take the derivative of a y. Okay, we're going to go ahead and practice some of these. Let's go ahead and check out maybe a picture example. So consider the graph of the circle to the right. Let's go ahead and find the equation of a circle. It's probably been a while since you've done this. Are there maybe certain things we can identify about this circle to perhaps help us write it?
Center point is
okay.
negative 2.
Okay, so there's the center. Anything else we can identify about the circle? Yeah.
Radius of 5.
Radius of 5. All right, so I think we can identify those characteristics on a circle, the center and the radius. The question is, how do those numbers, how do those values show up in the equation? I don't expect you to remember this. Okay, I would say it's not that important, but this is eventually going to be an implicit equation. Okay, x's and y's mixed in, which means we should be able to find the derivative of it using that implicit technique. Okay, can we perhaps really dig deep to think about how these numbers show up in the equation? Maybe I'll give you a little setup to help you out. You probably haven't done this since geometry, like years ago. Equals the radius squared. Okay, so the radius squared is on the end. What do you think, Dan? You want to try the next or the rest of it?
The first one will probably have x, and since we're in the positive, it would be minus 3.
Ooh,
and the next
okay.
one will have y plus 2 because we're in the negative.
There we go. Okay, so what you have is the center of your circle. That's basically telling you how the circle has shifted. Okay, instead of starting at the origin like everything typically does, this one was shifted right 3 and down 2. So in terms of transformations or translations, right 3 would represent a minus 3 on the inside. Now down 2, what we're used to is just a minus 2 on the end of an equation, right? Okay, but that's if the equation is in explicit form. If it said y equals something, then the minus 2 would be on the end. Since this is implicit, down 2 is kind of the opposite showing up here, just like the 3. Okay, so this is signifying right 3, down 2, and a radius of 5. Okay, the square root of 25. Don't expect you to remember that. Okay, but this is how these characteristics show up in an equation. So notice how this is implicit. We have x's and y's mixed in. This definitely does not say y equals something. So when it comes time to find the derivative of it, we're going to use our techniques, but every time we take the derivative of a y variable, we need a dy over dx. Okay, that notation or symbol. So think about this first term here. How do you want to find the derivative of that? We got a chain. So we'll bring down the 2, keep the inside. New power is 1 times the derivative of the inside, that next layer, which would just be 1, so you don't have to write that either. Okay, you can if you want to. But here's the derivative of the first term. Okay, let's go ahead and move on to the next one. Think about your techniques or your shortcuts. What do you want to do there? It's another chain. Doesn't it look kind of exactly like the one we just did, just with a y variable instead of an x? So we'll bring down the 2, we'll keep the inside, new power is 1, times the derivative of the inside. Right, the derivative of just y would be 1, just like the derivative of just x is 1. But since we took the derivative of a y variable, we need a dy over dx symbol. Let's keep moving. Derivative of 25? 0. Okay, I'm going to tell you guys right now, it happens every year. Okay, and I'm trying to nip it in the bud, but it happens every year. You guys get so caught up in trying to take the derivative of these individual terms that we forget to take the derivative of this last number. Okay, I am willing to bet my life savings that someone will write 25 here. Okay, just because you get caught up in it. Okay, but you have to keep taking the derivative all the way through. So if it is a number, realize that the derivative would be 0. Okay, I'm trying to catch you guys this year. Do we understand that? Okay, I know it's going to happen. I expect it to happen, but I'm just letting it be known so it probably doesn't happen. Okay, so we're done taking the derivative using our shortcuts, but we're going to solve for dy over dx because this symbol itself means derivative. So we want to eventually get dy over dx equals something in the end. Okay, that's our goal. So you got to think about some algebra techniques. How do you want to get that symbol all by itself? Can we start moving things to the other side? Let's see, can we take this first term and subtract it over? That 2x minus 3, subtract it over. All right. So then what do you want to do to get that dy over dx all by itself? Go, Brayden.
5 by 2 y plus.
All right, so we're going to divide this whole thing to the other side. So if we divide that over, maybe I'll go ahead and write it down and then we'll simplify it. So we have negative 2x minus 3 up top and then a 2y plus 2 on the bottom. 2's are going to cancel, but we're just left with a negative sign up top and then the x minus 3 quantity with the y plus 2 underneath. All right, so there's our cleaned up derivative. Okay, our simplified version, dy over dx equals something. All right, so if the equation we wrote at the top is representing the circle, then this derivative is representing what in terms of that circle? What does derivative mean? When I say derivative, you think slope of, yeah, slope of tangent line. Okay, and something that we looked a little bit further into in the last unit was a rate of change. Okay, so it's perhaps how this circle is changing or curving at some point. So that's what we're going to take a look at in this chart. Okay, So now that we have the derivative, which represents the slope, let's go ahead and think about some of these tangent lines on this circle. So complete the table below by finding the value of the derivative, okay, by finding the slope at the indicated points, and then we're going to draw what this represents on the circle at the top. Okay, so at this ordered pair, 0, 2, so on the circle we're kind of at this point right here. If we're going to find that derivative value, we're going to figure out the slope value. So how do you think we can use that point to help us figure out the slope? Is there something you just intrinsically feel like doing? If this is our derivative and this is the point, plug it in, right? If you have a point, it's an x and a y value. So if we were to plug in 0 for x and 2 for y, looks like we'll get 3 over 4. Okay, so what's that number representing again? If that's a derivative value, dy over dx, derivative is 3/4. That's the slope of a tangent line. So at this point on your circle, you should be able to go up 3 units, right 4 units. Okay, plot another point. Maybe you want to go the other direction too. Okay, down 3, left 4. And if you were to connect those points, you would create a tangent line. Notice how it would only touch once. Okay, so the slope or the derivative at this specific spot on the circle is 3/4. Do you think we can go through the other points as well and plot them on the graph? Okay, go ahead and give them a shot. How'd we do? Pretty good? All right. I know we got 3/4 together for the first one. Were you able to get 0 for the second point? All right. And graphically, if our slope is 0, what's going on the graph? It's a max or min, perhaps. Yep. And notice how at that point, aren't you at a maximum? You're at the top of the circle. And if you were to draw a tangent line, it would have a 0 slope, aka flat. So whenever your derivative is 0, okay, we talked about that phrase, we have a horizontal tangent, okay, a flat tangent line. What about the third point? You got -5 over 0, which hopefully we know is undefined. Okay, you can't divide by 0. What would the tangent line look like if you tried to draw it? Bless you. So we're at this point right here, 8, -2. Kind of the rightmost point, yeah.
You know that the slope is undefined, and you know that you could consider a vertical asymptote and draw it vertical.
All right, we have a vertical slope. Okay, the only way you can touch the circle once, okay, aka tangent line, the only way you can touch it once at that specific spot is to have a vertical slope. So instead of a horizontal tangent like the last one was, here we have a vertical tangent. Okay, and that's one of the kind of 3 spots we talked about where a derivative does not exist, right? We talked about sharp points, we talked about endpoints, and we talked about vertical slopes. Notice how we solved, or we showed, that the derivative does not exist. Okay, it's undefined. So graphically, at least in this case, we have that vertical tangent. So 2 things to kind of check out here that we're going to pay probably more attention tomorrow. Notice how when we have a horizontal tangent, okay, the top of the fraction was 0, okay, meaning the change in y was 0. So maybe we'll make note of that. Okay, the dy was 0. However, for vertical tangent, notice how the bottom was 0, meaning the change in x was 0. Okay, so we're gonna spend more time on that tomorrow. All right. We had another horizontal tangent for the last point or for the next point. Okay, we had a minimum value, a -3/4, so that's this guy right here. Another undefined slope, looks like we're at the leftmost point, so another vertical tangent. And then the last one was 3/4, this last one down here. We do okay? Perfect. Okay, so implicit derivatives. When you have an equation with x's and y's mixed in, we're still going to use the same shortcuts, but whenever you take the derivative of a y, you need that dy over dx symbol, okay, to signify a derivative. Let's go ahead and practice some of those equations. Okay, so no more graphs in this case. That was just a good kind of example of how the derivative relates to a graph. Okay, when you have an implicit equation, let's just look at equations for now. All right, so start on the left, work your way to the right, think about your shortcuts. How would you want to find the derivative of y squared? Power rule, chain rule, product rule, quotient rule. Power, right? We would have a 2y, okay? But we took the derivative of a y variable. So we immediately need to write a dy over dx. Let's move on to the next term, the derivative of 2x. We just have 2. Moving on to the next term, the derivative of 3y. Are we thinking 3? Okay, but we took the derivative of a y variable, so we need another dy over dx. Are we okay with that initial setup? Okay, now here's the tricky thing. We want to clean it up a bit. In the end, okay, we want to get a dy over dx equals something. Okay, the derivative is this, okay, whatever this might be. But if you notice in our equation, we have two of those symbols written. We haven't really seen anything like that just yet. So we're going to have to perform like some math magic here perhaps. We're going to have to turn two of those symbols into one of them at the end. Can you think about any algebraic technique that you could possibly use to go from having two things down to one? Yeah.
You could subtract 3 dy over dx and get 2y minus 3 dx,
Okay, so
as they both have a common multiple.
okay, so Dan noticed how, well, we're trying to get a dy over dx all by itself. So how about we get all of those on one side of the equation? Let's go ahead and move the 3 dy over dx to the other side. You could move the 2y dy over dx over, okay, but just get the dy over dx's on one side. I like that so far. Did you have a plan to keep going from there?
Oh yeah, because the dy and dx are common multiples, you could take them out and have dy over dx times 2y minus 3.
We're going to factor. Yep, factoring. Notice how they both have a dy over dx in common, which means we can factor that out. Okay, it's considered a GCF. So when you have those multiple derivative symbols in there, we're going to get all of those on one side. We're going to get everything else to the other side because we don't really care about that just yet. And we're going to factor out that dy over dx derivative symbol because it's a GCF. So we're left with a 2y minus 3. There's kind of the math magic part. We went from having two derivative symbols down to one. So now that we have one, how can you solve for it? How do you want to get dy over dx all by itself? Divide it over. Yep, divide the 2y minus 3 to the other side. All right, there's your derivative. So you might get a little worried when you have all of these dy over dx's showing up in your initial derivative, but don't fret, okay? Just get all of them on one side, everything else on the other, again, because we don't really care about it just yet, and we'll factor out that dy over dx. It should go away. All right, now I don't want you to write this down, but remember at the beginning Dan mentioned how we could use y prime instead of dy over dx as another symbol? I want to kind of show you why that might be a little confusing. So this first derivative step right here that we wrote, you could write it like this. Right? Y prime and dy over dx are the same thing. But some of you might get confused because you have these two y's here. And you might want to do something with them. Some of you might not write your primes clearly, and maybe you write them as powers of ones, which you might confuse for some power rules or properties later on. Okay? So if you want to use y prime, okay, I'm completely okay with that. But for most of us, I think we're going to prefer the dy over dx because it looks completely different than some of the other variables that are written in there. Okay, it's just going to make us be a little bit more organized. Do we kind of understand why this might be a little confusing? Because y prime and y look very similar. If you forget that prime mark, you're screwed. I'm just letting you know that right now. Okay, so I would prefer dy over dx, but that's just my preference. All right, let's go ahead and try this next one. Okay, work your way through. Notice how it's implicit. We have x's and y's mixed through. If I can spell implicit. Okay, so our first term, how do you want to find the derivative of 2x? Your shortcut? Yeah.
You just get a 2.
You just get a 2. All right, moving on to the next term. The derivative of e to a power. What's our shortcut? Yeah.
It's just e to that power times the derivative of that power, which would be dx over dy, or dy over dx.
There you go. All right, so e to a power, our derivative shortcut, is e to that power times the derivative of that power. The derivative of y is 1, just like the derivative of x is 1. But since we're taking the derivative of a y, we need that dy over dx symbol. Every time you take the derivative of a y, you need to write that in there. All right, let's keep moving on to the next term. The derivative of x squared. Yeah,
2x.
2x. And then we're going to subtract the derivative of y squared. Yeah.
2y dy over dx.
dy over dx. We took the derivative of a y variable. All right, so notice how our goal is to eventually get dy over dx all by itself, okay, equals something, but we're going to have to use some algebra to help us get us there. So we have multiple dy over dx symbols in our derivative. We're going to move all of those to one side, everything else to the other, and then use factoring to help us go from 2 down to 1. Okay? So I don't care how you maneuver it, okay, how you move things, you just have to do it in a way that you're comfortable with. So where do we want to go from there? Do you have a preference? Yeah.
You can have 2 minus 2x on one side, the left.
Okay, so Dan,
Take out the 2.
there you go. So Dan wants to move this 2x over here, which therefore means we'd have to move the dy over dx term to the other side. You could switch them that way. Okay, you could do the other two terms and switch them. It doesn't matter. Okay, so let's go ahead and do that. We'll move the 2x to the other side, so it'd be subtraction, and then we'll move the e to the y dy over dx to the other side. That would be a subtraction as well. Okay, so we have all of the derivative terms on one side, everything else on the other. We're going to go ahead and, yeah.
You can, well, I did it a little differently, not differently from that. Like I did the 2 minus 2x, and I just re-swapped them around to get
That's fine.
-2 plus 2, and took out a -2 to get -2, and then x minus 1.
There's a lot of things that we could do. All right, we'll go ahead and pick up from there. Okay?
Which I think it does play a role later, hence why I did it.
We'll check out some more examples tomorrow. Okay? Implicit again, x's and y's mixed in the equation.